Imagine trying to map every single concept, skill, and insight you acquire over a lifetime. You would be building a massive, dynamic knowledge graph, a sprawling web tracking your intellectual development in real time. But to build an AI tutor that can actually navigate this lifetime of data, we run straight into a hard engineering constraint, the LLM context window. Human lives generate near infinite data, but large language models can only hold a finite number of tokens in active memory at any given moment. Here is the bottleneck. If you try to shove an entire unoptimized map of your life into an LLM's prompt, the system breaks down. The context window overflows. The model loses track of crucial details in the noise, leading to hallucinations and degraded logic. Building a lifelong AI tutor depends on the architectural strategy for context management rather than the raw reasoning power of the model itself. To solve this bottleneck, we have to rethink how the data is structured. The solution is an architecture known as a multi-resolution cognitive map. Semantic zooming organizes your knowledge into a strict hierarchy. It uses a technique called lazy loading. The system maintains a low-resolution map of everything, but only renders the high-resolution details when it zooms in on a specific area for immediate interaction. This dynamic retrieval structure relies entirely on graph database structures and context management techniques that engineers can deploy right now. Before we look at back-end routing, we must understand how the user experiences this map. To prevent cognitive overload, the front-end interface must be highly spatial and fluid. This interface layout is what we call the orbital view. It represents the macro level, displaying only the highest level domains of a user's life, broad categories like technology, philosophy, health, and career. The visual properties of these nodes act as metadata. By growing or shrinking, shifting in color or brightness, the interface shows the user exactly where they have momentum and which areas are suffering from decay. When the user selects a specific domain to work on, the interface shifts to the focus view. The main node expands to fill the screen, revealing the fine-grained milestones housed inside it. Simultaneously, the non-active domains recede into the deep background. They are still tracked by the system, but they are visually minimized to eliminate noise. Inside the focus view, the system uses a now indicator to map progression. The path behind the user is a solid line, representing mastered concepts. The immediate task pulses rapidly as the active now node, and the steps ahead are kept as faded outlines, marking the frontier of their understanding. By visually collapsing distant domains, the interface reduces the cognitive load on the user. However, maintaining this focused view requires a back-end routing engine capable of assembling the right context without exceeding token limits. A standard static retrieval augmented generation pipeline cannot power this interface. The system has to dynamically assemble prompts based on the user's immediate cognitive state. The first state is deep work. It triggers when a user enters a flow state to study a complex topic, like debugging algorithms. In this split-screen view of the database, the retrieval logic is deep and narrow. The graph isolates exactly two things: the micro-headings of the current active node and its immediate parent heading for local context. Those specific data points slide into the context window to form the prompt. Notice what is excluded. The system pulls zero information about the user's other life domains. Starving the prompt of macro data dedicates maximum token space to the fine-grained technical details required for surgical tutoring. The second cognitive state is task switching. This activates when a user finishes a session or starts a new day and needs to know what to do next. Looking at the updated graph, the retrieval logic flips to shallow and broad. The top layer of the entire graph illuminates, grabbing only the level 1 and level 2 macro headings across every domain simultaneously. These high-level nodes slide into the context window, giving the LLM a bird's-eye view of all the user's active life categories. The system then injects supplementary metadata. Small tags for time since last interaction, current momentum, and user energy levels attach themselves to the nodes. By retrieving this broad dataset, the LLM acts as a life orchestrator. It can analyze behavioral imbalances, like spending 6 hours straight on coding, and suggest a healthy pivot to a neglected domain. The third state is cross-pollination. It triggers when a user asks a question bridging two subjects or struggles with a new concept. This requires an asymmetrical multi-branch retrieval logic. Here, the database highlights two completely separate branches. On the first branch, the query burrows deep to isolate the high-resolution micro-headings of the new target concept the user is struggling with. On the second branch, it targets medium-level headings from a completely different domain that the user has already mastered, and a line connects the two disparate areas. Deliberately connecting these distant nodes allows the LLM to generate highly personalized pedagogical scaffolding. It can pull a strong analogy from a domain you already understand to explain the exact mechanics of a domain where you are weak. The final cognitive state is long-term goal alignment. The system utilizes this during monthly reviews or when a user indicates they are feeling lost. In this timeline view, the retrieval logic relies on the path graph. The database connects a series of major nodes stretching backward in time. The system pulls the sequence of completed major headings over a defined macro timeline, like the last 6 months, and projects that path forward toward a massive node representing the user's ultimate goal. The prompt completely strips out the daily microtasks. It isolates only the major milestones to map them against those ultimate objectives. By strictly gating out the microdata, the LLM is forced to adopt the persona of a high-level product manager. It assesses if the user's broad trajectory is actually moving them closer to their ultimate life goals. When you step back, the complete architectural loop becomes clear. It starts when a user takes an action, which triggers one of these 4 state classifications. This flowchart demonstrates how the classification directly dictates which of the 4 graph traversal algorithms the router executes. The algorithm isolates the exact required context and flows it directly into the LLM context window, generating the optimal prompt without wasting a single token. In the final step of the loop, the front-end UI updates to show the state change. The active now node advances, leaving a solidified mastered path behind as the data graph evolves. Structuring data as a multi-resolution cognitive map solves cognitive overload for both the human learner and the underlying machine model. Combining hierarchical graph databases with dynamic state-dependent prompt assembly provides a viable technical path for developers to build this system today.